Hello and welcome. In this presentation, which is topic 10, we are looking at unknown input observers designed for a time delay system where we only use delayed output vector. So we have this time delay system, and the output measurement vector, as you can see, contains only a linear combination of the delay stack vector. So this is a very special case. And we would like to know whether it is possible to asymptotically estimate the unknown input. Now, the situation where the output measurement vector contains only a linear combination of the delay stack vector, we can interpret one particular situation for that according to the following representation. So we can have the unknown input enter into the system, and it's a time delay system, and the output, the one from here, the output measurement vector itself, uh, in fact, contains linear combination of instantaneous stack vector. Now, it could be the case that the information, the measurement vector, is being delayed by tau, or it could be that the information output measurement vector here is actually is being transmitted over a communication channel where there's a time delay tau associated with it. And therefore, at the end of at the receiving end here, that's where it is used to reconstruct the unknown input. And so the measurement vector at this end here is actually the delayed version of the output measurement vector at this point here. Okay, so that might be one particular situation. And so the question here is, can we asymptotically estimate the unknown inputs? In other words, can this unknown input observer located in here where it used the delay output measurement vector, can we reconstruct asymptotically the unknown input? Now, the answer to that is no, it's not possible because of some issues that we discuss later on. Particularly, it's something to do with non-causal property of the signals. So what we can say here is we can instead estimate asymptotically a delayed unknown input. So we can achieve this objective here as t goes to infinity. We can't estimate instantaneously. We can estimate a delayed version of the unknown input. Okay. And so we will discuss some possible investigations in the future that how can we achieve this objective. But at the moment, let us consider development of how we go about design an unknown or a delay unknown input observer to asymptotically estimate this delayed unknown input. So the unknown input is only known as a delay time. And the development in this is basically in chapter 6 in the book. So let's go to chapter 6 in the book. And it's address this specific situation. You got delay output vector. Okay, so we call this a delay output vector. Because as you can see, this output measurement vector does not contain any linear combination of the instantaneous stack vector. So we want to still achieving the seamless structure for the unknown input. And in that situation, we aim to use the first derivative of one output measurement only. So when we look at this output measurement vector, it contains p output measurements. And out of that, we pick one and we code yi of t. Let me code yi of t. And this y of t is selected if this condition is satisfied. In other words, the row CDI, which is the ith row of matrix CD, multiplied by D, has to be non-zero. So that is associated with the matching condition. Okay. So um, if that situation can actually be met, then we're going to pick an output measurement vector. No, output measurement, yi of t. And we will use its first derivative for the reconstruction of the unknown input. The unknown input that we're going to reconstruct here is going to be a delay version of the instantaneous unknown input, delay version of it. So we're going to use the same kind of stack transformation, the matrix decomposition like what we discussed earlier. Okay. And we can even make the presentation simplicity. We can assume that matrix CD is of canonical form. Okay, and so when we actually do our matrix decomposition or unknown input decomposition technique, we come up with the matrix transformation T of this form. And then E has a specific structure because matrix CD in this particular form. And if we pick the first output measurement to be the first one, then matrix is this form. Otherwise, it's just basically the null space of the matrix V1 C, V1 times C. Okay. And then this metric V here is invertible, and so we have a specific structure for metric P. So all of this is based on our previous metric decomposition. And now, once we apply that kind of transformation into the time delay system, we obtain these equations. And again, as we can see, the metric D is basically appear, not the metric D, the unknown input D of T appear in this equation, whereas in here is actually does not appear there. Now we also doing the pre-multiplying both sides of this equation by this inverse of matrix V, and all of these usual identities, which is the result of the inverse matrix V times matrix V itself, we have the following equations. So what we can see in here is we obtain the output measurement vector, which is also containing the delay combination of the delay stack vector of a smaller dimension, x bar 1 of t. This is a vector which has a dimension 1 less than the original vector. Now, the thing about this decomposition is that when we have this expression, and when we substitute it back into equation 646, which is the one in here, this is so that we can obtain explicitly an expression for the unknown input. We obtain this expression here. So because this combination of the output, in other words, it's basically the first output y1 of t is actually the delay version of this stack variable. So that means that if we want to express x bar 2 of t, then it's actually depending on the future output measurement. So it basically, um, we have this equation here. Right. And then if we substitute it back into this equation, we can see that there's this term in here, and also this derivative term in here, which is basically the derivative of this um, output measurement y1 of t plus tau. And so we have in this situation here, okay, the unknown input itself is expressed in terms of the first derivative of the future output measurement y1 of t, and as well as we got this v1 yt plus tau, which is basically y1 t plus tau. So the instantaneous, in other words, the expression for the unknown input itself, we have this kind of difficulties in here because the present value of the unknown input is basically is in terms of the future output measurement y1 of t and y1 of t dot plus tau. So this is where we're talking about a non-causal problem, because we can't obtain a future output measurement y1 of t at time t. Okay, so that is the situation. So as we can see that under the situation where the matrix C, in other words, the information that is available to us at this point here, and if it depending on the delay combination of the delay stack vector, then it's not possible to obtain or estimate instantaneous. I will talking about instantaneous. That means the the of t in here. So as we can see that the way we pose this problem or the situation that we will address in this discussion is that this problem is still an open problem for future research. In other words, because of the non-causal problem in here. So that tells us that, look, if we want to estimate this unknown input, instantaneous unknown input, we can't do it based on this kind of decomposition in here. So what we can do is to estimate the unknown input, but after a time delay tau. Okay, so that means that if we look at this expression here, and if we delay it by tau, we delay it by tau, which means that we got dt minus tau, and therefore this expression here becomes y dot t. So it's actually realizable. This is basically the first derivative of the output measurement y1 of t. And similarly, this expression here is now becomes v1 yt, which is realizable because that is basically the output measurement y1 of t. And then the rest of them, like for example, we got this one here is going to be delayed by tau, and this is going to be delayed by tau, and this is going to be delayed by 2 tau. So we have this expression. So we can see that based on our metric unknown input decomposition technique, we can overcome the non-causal problem by looking at an expression of the delayed unknown input. And then when we look at these two terms in here, you can see that the two terms in here basically combination of the delay stack vector x bar 1 t minus tau and x bar 1 t minus 2 tau. So it's a generalized functional, as you can see that. It's a generalized functional, and this generalized functional is a combination of the delay. See the delay stack vector x bar 1t and the delay stack vector x bar 1t minus 2 tau. So that should not be an issue for us, because what we can do then, we can say, look, we can actually design a functional, a generalized functional observer to estimate this generalized functional directly. And that's what we say in here. And if we can do that, then the delay unknown input. Talking about delayed unknown input now. And so it can then be realized. And it's basically the first derivative of output measurement y1 of t. It's first measurement y1 of t and its delay version of it, and this generalized functional. Okay. So that's the situation there. If we are facing with the problem of estimating an unknown input for a time delay system, where the output measurement vector does not contain any linear combination of the intent and the stack vector, according to our matrix decomposition, we can still realize um, a delay version of the unknown input, a delay version of the unknown input. And it's also in the form of the first derivative of one output measurement. That's what it is there. It's realizable, realizable, realizable. And then if we can estimate this generalized functional, then we can actually estimate. We can't estimate instantaneously the unknown input. We can only achieve estimation of the delayed unknown input. So in other words, uh, after a certain time, the unknown input observer, estimate that delay unknown input. Still something, still something. However, the instantaneous estimation is not possible because of the non-causal problem. Okay, so then we say, all right, in that case, let's look at some cases. Let's examine how we go about designing an observer to estimate this generalized functional. So have a look at this generalized functional. It's actually delay stack vector here and delay stack vector here as well, combination of that. So we look at the structure of matrix A bar 1, 2. Why do we look at that? The reason for that is because when we look at this equation here, which is basically a system itself that does not have the unknown input, and we have this term in here. And we have this term in here, and we realize that if we have x bar, if we substitute x bar 2t in here, x bar 2t in here, this uh, variable in there, and this happened to be depending on the future output measurement of y1 of t, then there is a problem with that. You see? So that's why we say, okay, we basically investigate this situation in here, and we say, all right, in that case, how about this one equal to 0? So this is called the structural constraint on it. And if this is equal to 0, then from this equation, we can realize the uh, reduced order system without unknown input. because now that one is delay version of it, and it's actually equal to this expression there. So we can get uh, a disturbance-free time delay system, which is this system itself here. Okay. And of course, the output measurement vector y bar of t is again a linear combination of the delay stack vector. So we have this reduced order time delay system, and this is the one that we should design an a generalized functional observer to realize this one directly. Okay, and so what is this expression? It's actually uh, the one given in here. So when we look at it, we really have a time delay system with delayed output measurement vector, and the functional that we want to realize, the functional that we want to realize is in fact depending on a linear combination of x bar t minus tau and x bar t minus 2 tau. And we developed a method which was discussed in the last topic, if you recall it. In the last topic, we were looking at the discussion where we design generalized functional observers for time delay system with or without delay output measurement vector, which is this form. That was where the metric c equal to 0. And the functional that we have in here is a specific situation of the generalized functional that we discussed in chapter 16. And that where f here is 0. Because when we look at this generalized functional, it does not contain the instantaneous stack vector, combination of the instantaneous stack vector x bar 1 t. To design a functional observer, a generalized functional observer for this system, this is possible because the theory or discussion were done in chapter 16. Okay, so that is one situation we can actually employ the methods presented in chapter 16 to realize this generalized functional directly for this time delay system. And that's where we just simply looking at looking at this equation, and then we encounter this situation, and that's why we say, how about this one equal to 0? So this is done by visual inspection. We can verify it easily. Now the other situation is what happens if that doesn't satisfy the situation? Then is no problem at all. We can actually address a more general situation where this constraint is not satisfied. And so what do? In that case, we consider, this is the thing, we consider this system, but then we consider a delay version of this system, which is x bar 1 dot t minus tau. So, and then we got this thing in now t minus tau. This is now t minus tau, and t minus 2 tau, and t minus 3 tau. I mean, 2 tau, sorry. And so what happened in there is we say, no problem, we delay it by tau. Okay. So we got this time delay system itself in here. So we consider that. And because the output measurement vector, y bar of t, we know it. It's this form. So we're going to say, look, let's look at this reduced order time delay system with no unknown input. And so we can then design a generalized functional observer to estimate this generalized functional. which is z hat tau t there. And that was given in this equation here. All right. So we basically say, all right, we apply existing results we discussed in the chapter 13. We can then design a generalized functional observer. And also it's a special case of sections of chapter 16. And when we look at this, it basically this now team and a tau. So this is team and a tau. So we can have a specific special case from chapter 16. And then we can realize a delay unknown input for the estimation. And the theory behind all of the generalized functional observers actually been discussed in chapter 16. Okay, so in summary, when we have the time delay system, the output measurement vector is being delayed or it contains the combination of the delay stack vector, we can only estimate a delay version of the unknown input. And to realize the delay version of the unknown input, we have two cases. Of course, case one is just a special case, whereas case two, we can just use it straight away. We basically have in this time delay system. And we estimate a generalized functional observer for it. And so that's basically the idea behind that. Okay. And so we can look at numerical examples and bear in mind that the unknown input is the one that estimates this delay version. And so in this numerical example, we have the matrix CD, and then we do the decomposition, and then we realize the the unknown input by estimating this generalized functional. And in this example, is given in such a way that the constraint on this bit here is basically 0. So we apply case 1. And when we apply case 1, we can use the results discussed in chapter 16 to realize the generalized functional observer for it. That's what the one discussed in numerical example 5. And then we realize this delay unknown input, the estimation of this delay unknown input. And that's basically the way how we can realize it. And we can show the simulation results. And when we look at the simulation results, we can see that the dark solid line here is the instantaneous unknown input. And we can only estimate a delay version of the unknown input, which is shown in these two figures in here. Okay. So we got the red line is the delay version of the unknown input, and the dot blue line is the asymptotic estimation of it. So unfortunately, we can't estimate the unknown input instantaneously, only a delay version of it. So we know information about what happened to the unknown input that enters into our system, but only after a certain delay time. And then there is also another numerical example where the constraint here is not satisfied, and so we apply just these results in here. Which is case 2. So we consider design a generalized functional observer for this time delay system. And so it's also give us an asymptotic estimation of a delay version of the unknown input. Yeah. So that's where the situation of delayed output measurement actually impact on the estimation of the unknown input. Okay. As you can see, we don't know yet how to estimate instantaneously, how to estimate instantaneously. And so that is a problem in which remains an open problem. Now, if we just look at the expression of the unknown input, this is something we actually thinking that how to overcome the non-causal problem. Okay, how to overcome a non-causal problem. Now, the issue that we have in here is the expression for the unknown input depending on the future output measurement of the measurement y1 of t and its derivative, its first derivative. If we can just think back of the last topic where we were discussing the estimation of some of the stack variables instantaneously, where the output measurement or the output measurement vector uh, contains only the delay version of it. If you can recall that. That was the situation where this matrix C equal to 0. And so that was in chapter 16. At that chapter, we actually demonstrated that it's still possible to estimate instantaneously the stack variable, so the stack vector of a time delay system where the output measurement vector is being delayed. Now, if it's possible, then we might be able to use that kind of observer first to estimate instantaneous. That means that the future, because have a look at the output measurement in here is actually a delay version of it. So if we look at the future, that means yt plus tau. Then yt plus tau is in fact a linear combination of cdx of t. And so we are thinking, speculating that it might be possible if we can somehow first design an observer, a generalized functional observer, to estimate a linear combination of the output instantaneously based on the delay output measurement. Then if that's the case, for instance, in here, we design an observer to estimate the information about the stack variable x1 instantaneously. And then if that's the case, that means we know this information, and therefore we can realize it first derivative. And maybe then it's possible for us to realize the estimation of the unknown input instantaneously, instead of the delay version like what we discussed in here. That is something for the future investigation, the problem for us to investigate in the future research endeavor. Okay, so so that where we like to stop here for this particular topic. So we address the situation where the output measurement is being delayed. I mean, in other words, it does not contain any instantaneous combination of the instantaneous stack vector. And so as best at the moment, we can only estimate the delay version of the unknown input asymptotically. It's still a useful outcome. an open problem is how to do it instantaneously. Okay. Now, so in the next discussion, in the next presentation, we're going to relook at the unknown input observer design problem, which we discussed in chapter 5 in this book. And remember, at that time, we was just putting a constraint on the matrix CD, and we say that we need to have V1 CD, something along that line, constraint 1 is equal to 0 in order to explicitly express the stack variable x2 bar t. Now we're going to relook at that situation. Okay, so that there was a constraint we put on matrix CD, and we want this one to be satisfied. And if it's satisfied, we got two constraints, and then we realize a whole heap of um, different, two different type of time delay systems, reduce other time delay system with no unknown input. And it's a combination of multiple time delays and so on. Now we're going to relook at this problem, and we try to see whether can we overcome these constraints. Okay, and that's what we're going to discuss in the next presentation. Okay, so thank you very much for joining, for watching, and I see you again in the next video. Okay, so bye bye for now.